Good morning and welcome back to microprocessor course, lecture number 13. In today's class, we're going to continue with memory system. If you still remember our last class, we started with memory system. We have learned about the different types of memory. We went through the memory hierarchy. And in today's class, we're going to continue with memory. We're going to learn different method for accessing data, and I'll introduce you also the cache memory and the different caching memory mappings. Because we know that the memory, main memory is bigger than the cache memory, we need some caching techniques, mapping techniques to allow different memory blocks to map with cache lines. But before today's class, I want to check on your attendance. Class 5, number 1, 2, 3, 4, 5, 6, 6, 7, 8, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20, 20, 21, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Class 6, number 1, 2, number 2, number 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 15, 16, 17, 17, 20, 21, thank you, 22, 23, 24, 26, 27, 28, 29, 30, B21, 6, 15. Good. Now, if you still remember from our last class, we went through the memory system. We talked about the memory hierarchy starting from registers. Registers, which are the smallest memory in our computer system, but they are the fastest one. They are smallest memory in our computer system, that they are really fast. These registers are there to store data and instructions that are being processed by the computer system. After registers, we have the cache memory. Cache memory. And the cache memory is outside of the central processing unit. It has to store the most frequently data. And depending on the technology, we have different levels of cache. Level 1, level 2, level N. And each level, this level 1 is smaller than level 2. Level 2 is smaller than level 3, but as the size of the level cache memory increase, the speed decreases as we have seen from the memory hierarchy. So the cache memory is there to store most frequently data. Now, after cache memory, we have the main memory. The memory which is there to store active data. Active data. Then these are what we call volatile memory. Which only hold data when there is a power. If there is any interruption of the power, the data will be lost. Now, because sometimes we needed to store data permanently, this is only for temporary storage. Sometimes we need to store our data permanently. We need secondary storage to store our data permanently. So there might be some more levels of the memory depending on the technology. We may have tertiary storage depending on the technology being used for the system. Now, this is in short the memory hierarchy that we learned from the last class. And if you still remember, we also talked about the different memory types. We talked about the RAM, random access memory. We talked about different types of ROM. And here we have talked about DRAM memory. This store data in form of charge on capacitors. That means it needs to be periodically refreshed to retain its data. So we have another type of RAM that we call static RAM, SRAM. This one use logic gate to store data. That means it doesn't require to be refreshed to retain its data. We talked about flash memory and other types of memory. Here for read-only memory, we talked about PROM, EPROM, and other types of read-only memory. So in today's class, we're going to continue about memory accessing techniques. How does the CPU access data from the memory? And I will also introduce the cache memory and some cache memory mapping techniques, because we know that the cache memory is smaller than the main memory. Not all the main memory blocks can be in cache memory. So we need to use some caching techniques to map the main memory blocks into two specific cache lines. Now, let's get it started. If you still remember, we talked about a memory. This is just a review. A memory is a very component of computer to store data and instructions. That means it allows the data to access information during the program execution, during task execution. So it has to hold, for example, operating system, different applications, data being processed, and so on and so forth. So that means that the efficiency of any computer system largely depends on how fast and how efficiently the memory system can support the data. So when it comes to the computer performance, we do not only consider the CPU, the central processing unit. We also needed to take into consideration about the memory performance. We have seen that the efficiency of the computer system depends largely on the how the memory system works, or how fast the memory can retrieve the data or can store the data. So that means that the whole performance of the computer system does not only depend on the central processing unit, we also need to take into consideration about the memory access time and other factors that are linked with the memory system. Now, how does it work? How does the memory work? We have the memory, and we have addresses, and each address holds the value. Now we have here memory organization. This is for address, memory addresses, memory location, and these are varies. Now here we have memory addresses, let's say from 001 up to FF. Then here we have different varies. That means that we have memory addresses. If you still remember in which number system we have our memory addresses addressed in which number system we have the memory addresses expressed in. Which number system here? If you see OX means what? OX. Huh? This means what? This one. Huh? You don't still remember this? If I do this, this means what? Huh? You don't still remember this? Huh? Load this into AX. So this is a what? This is a binary number, this is hexadecimal number, this is a octal number. This is a what number? In which number system we have? You have this OX to indicate hexadecimal. So we have our memory addresses, which are expressed in hexadecimal. We have this memory location, this memory address, which hold this data. That means to get access to this value, the CPU will use this memory address. To get access to this data, the CPU will use this memory address. That's why we see data is stored in memory locations, is stored using memory addresses, and each address has a unique address. So there is no duplication in memory addresses. Each location has its own memory location, its own memory addresses. So that means that each address is unique. Now, the CPU access memory using these memory addresses, using these memory locations. For example, if the CPU wanted to get access to this data, it will specifically have to use this memory address 0x01. So I want to retrieve the data at this memory location. Now, without memory, the computer cannot execute all the programs that it has, or it cannot process the data, because it can't hold all the data that it has on its hand at one time. It cannot process all the data, all the instructions at one time. So we need a memory system to store the data and the instructions. Now, there are some issues. There are some issues in the computer system. What is the fastest computer component that we do have? which component of the computer system? We learned about the different components of computer system. Which one do you think is fast? We have the processor. We have the central processing unit, which has a speed which continue to increase very fast, which means that the processor, the central processing unit, is improving very fast. But we know that the memory access time speed does not improve at the same speed as the CPU is speed. That means that there are some challenges that are linked with designing the memory. So we need to have some memory trends, including the synchronous RAM, to provide fast memory access time. We also need to redesign the DRAM chips to provide higher bandwidth if you compare to the previous memory system. So we also need to have structure of the code that needs to increase its locality, and using some prefetching techniques, for example, to make the cache memory visible to our instruction set architecture. So these are some issues that are linked with the computer system now, because the speed of the central processing unit is being increased at a high, very speed, a higher speed, if you compare to the memory speed, if you compare to the memory access time. Now, we needed to have a large and a fast memory. This is very important. We needed to have a fast and large memory. Large because as there are some advancement in software, we needed to have a big memory size which can help us to store much data as we want, and instruction as well, but the memory needed to have less memory access time if it comes to store data to the memory or retrieve data from the memory. So this is a challenge. We need a large and a fast memory system. So we have DRAM, for example, dynamic random access, which store vary as the charge on capacitors. But this one, as I have said, it needs to be periodically refreshed to retain its data. We have seen that the SRAM is smaller, but this one stores data using logic gate. It doesn't need to be refreshed any time to maintain its data. So we may have to use a static RAM to store data using a pair of logic gate, and it is faster, but if you compare to the DRAM. It has to include 4 to 6 transistors per bit, and this type of memory, this static RAM, is mostly used in cache memory, as we have seen from the memory hierarchy. Now, we have a simple picture here, which depicts the different components of the computer and the speed. Now, we have the processor, which has a higher speed, and we have the memory. Here we can imagine this is the cache memory. As you can see, they are very small. We have our register memory here, which integrates in the processor, and we have the cache memory, which is also smaller and is faster than in the main memory. Then we have the biggest memory here. It might be the second storage memory. And as you see, as the size of the memory increase, the cost per GB decreases, and also the speed of the memory decreases. So there are three different factors that we need to take into consideration when we talk about memory. We have to talk about the size of the memory, the speed of the memory, the cost of the memory per GB. This is very important if you are discussing about the memory. We need to talk about what is its size. As I said, we need a larger memory system, but also with a higher speed. So we also needed to talk about its cost, because as its speed increase, as also also its cost per GB increases. Now, here we have memory technology and the memory access time. We have the static lamp. The static lamp, SLAM, is access time, memory access time for static RAM is between 0.5 nanosecond up to 2.5 nanosecond. And you see that the cost per GB is between 2,000 USD and 5,000 USD. That was in 2012. We have also DLAM. DLAM with is memory access time, which is 15 nanoseconds up to 70 nanoseconds. And you see that its cost per GB is decreasing if you compare with the DLAM that we just seen. We have the magnetic disk. The magnetic disk is memory access time, you see, is 5 microseconds up to 20. And is cost per GB is less if you compare with the DLAM. So we have to talk about access time, capacity, and the cost per GB. This is very important if you consider the memory factors. These memory factors are very important when it comes to discussing memory system. We have a clear summary about the memory technology. This includes the typical memory access time, and the cost is per GB. So this is just what we just learned previously. We have the SLAM, which has a very less memory access time. It comes secondly the DLAM, and you see that the cost per GB is being decreased as the size of the memory increase and the speed of the memory decreases there. We have the flash memory and magnetic disk. Now we're going to talk about principle of locality. Principle of locality. Why we do need to talk about this principle of locality? Normally, principle of locality or memory locality indicates the tendency of a memory to access the same memory locations. Let's say the memory location which are being frequently accessed. So we needed to talk about the principle of locality for memory to understand the tendency of a program which has to access the same memory locations or the same nearby memory location with a short of time. Now, when it comes to exploit memory locality, this we have to improve the cache performance, the cache memory performance, as well as the overall computer system. Now, if we talked about the computer principle of locality, we needed to understand that exploiting this memory locality, we have to improve the cache performance as well as the whole computer performance. Now, we have two types of memory locality. We have temporal locality and spatial locality. This means that for temporal locality, we have items that are recently accessed, which has a higher probability to be accessed again in near future. This is what we call temporal locality. We have some data items. These data items were frequently accessed. These were recently accessed. This means that there is a higher probability that they will be accessed again in the near future. For example, if you do use a loop, we needed to use a loop to allow us to execute the same instruction multiple times. Now, using a loop, this is a simple example of temporal locality because we have the data items. Let's say the data items, you use the loop to get access to array items. That means the items that are accessed recently, there will be a higher higher probability that they will be accessed again in the near future. The same goes for induction variables. Is also another type of temporal locality. For spatial locality, we have near items, near data items, for example, near data items that are near to the recently accessed data items. They are more likely to be accessed in the near future. So let's say we have sequential instructions access on data. That means that you have to access data from one memory location to the next memory location. That means if the CPU has accessed the data which is at memory location I, there is a high probability that the next memory location I plus 1 will be accessed. So this is what we call spatial locality. Example, we have spatial locality. For spatial locality, we have sequential instruction access all array data. Now we have the time t. Here we have a very simple diagram to depict this principle of locality. We have the time t and we have the probability. Time t on x-axis, and we have the probability on y-axis. That means that for temporal locality, items that are frequently accessed, that are recently accessed, they have a higher probability to be accessed in the near future. You see, if there is any item at time t1, if it is accessed, there is a higher probability that it can be accessed in the near future, again and again. This is, for example, instruction in a loop or induction variable. For spatial locality, we have items. These items that are near the recently accessed items, they are likely to be accessed soon. As it is depicted by this picture, we have the time t, and we have the probability to access the data which are recently accessed, all data which are near the recently accessed data. Now, what are some advantages of using this locality? Principle of locality. We just seen that the memory locality indicates the tendency of a program to access the same memory locations, all nearby memory locations. So some advantages are we needed to copy recently accessed data items from the disk to the smallest memory, let's say to the DRAM memory. So this we have to help the CPU to get access to the data in less time. So we need this because it can help us to export this memory locality to improve the cache performance. If you do improve the cache performance, that means that the overall computer system performance will be improved. Now, some of the advantages of using this principle of locality in a memory system is to improve the cache memory performance. By improving the cache memory performance, we are trying to improve the whole computer system performance. Now we have probability distribution for next memory access. Now this picture on the screen mainly shows a probability model of the next memory access. That means the current address is the center of the distribution. So this is the center of the distribution. This is the current memory access. Now, what's next? The height of the curve decreases as you move away from the center. Now, you see here, we have instruction address distribution, and this is the center. We have the curve. This is the peak center. We have the curve which have a high height to mean that we have a higher probability to access the nearby instruction. So if you move away from this center, from this peak, you will be able to see that the data or the instruction which are far away from this distribution center, they have a low probability to get accessed in the near future. The same goes for data address distribution. Now, this is the center for the distribution. That means the data items that are nearby this data address distribution, which is the peak, they have a high probability to be accessed in the near future. Same goes for the instruction address distribution, which is on the left of this diagram. We have the center. This is the peak distribution. The instruction address which are near this peak center, they have a high probability to be accessed in the near future. But as you move far away from this center, you move far away from this center, you see that the instructions that are far away from the center, they have a low probability to be accessed in the future. If you go far away to the left or you go far away to the right, you see that the instruction addresses that are far away from this center, they will have a less probability to be accessed in the future. Now, the same goes for the data addresses. We have the peak here, this is the center. We see that the data addresses that are near the peak, the center, they have a high probability to be accessed in the near future. If you see here, if you move far away from the data to the left or to the right, these data addresses, they have less probability to be accessed in the future, and so on and so forth. So this is the probability distribution for the next memory access. Of key characteristics of computer memory system. If you still remember, we talked about processor registers. Processor registers are example of internal memory. We have internal memory. We have external memory. So we have internal memory include the registers, include also cache memory, include also the main memory. This is based on the location of the memory in the computer system. We have internal memory, processor registers, cache memory, and the main memory. When it comes to external memory, we have disk, magnetic disk or optical disk. We also have tapes. These are external memory. Now, when it comes to capacity, we can talk about a word, which is a 16-bit. Number of bytes, we talked about this. Given the total number of bits in data weight, given the total number of bits in address bus, we can calculate the total number of word pair. We can calculate the total number of words. We can also calculate the total number of bits in memory. We can also calculate the total number of bytes in the memory as well. So these are more related to the capacity of the memory. The next one, we have units of transfer. We can use a word, or we can use a block of the data. These are some of the units of transfer. The next one is about access method that we're going to learn shortly. We have sequential access method. We have direct access method. And we have random as well as associative. These are the access method of data that the CPU uses to get access to the data stored in the memory. Now, when it comes to the memory performance, we needed to talk about memory access time. What is the memory access time? We needed to talk about the cycle time as well as the transfer rate. So these are more related to the computer memory performance. Now, physical type of memory: semiconductor memory, magnetic memory, optical memory, and when it comes to physical characteristics, we have volatile memory and the non-volatile memory, erasable memory and no erasable memory. Then we have also to talk about memory organization to understand how our CPU can select a word out of millions of words. We talked about memory organization shortly in the previous class when we talked about the current address strop and the low address strop. We're going to continue about this when we be talking in more details about memory organization. Now, unit of transfer. We're going to start with unit of transfer. We talked about word, a word which is a basic unit of memory organization, if you still remember. We have our memory which organized into words. The CPU will have to select a word out of million of words. We have here, if you still remember, we had a memory organization type. We have memory organization type. These are words. We have word number 1, word number 2, up to word number 512. These are words. And at each time the memory wants to read data from the memory will select a word out of a thousand of words using what we call low address strop. And once this low address strop is selected, the CPU will use what we call colon address strop to specifically select a cell. Out of a number of cells. That means if it is selected this cell, the main content that the CPU will be looking for will be here. We have 2, 3, 4 up to 512 as well. If we have a 2.n times 2.n, so that means we're going to have 2n times 2n. So we have this basic unit of organization, which is a word, is also equals to integer size and the instruction length. So there are some exceptions. Here we have 64-bit word or 46-bit integers. Now, when it comes to addressable units, this is the smallest one and can be individually addressed. We have a word. We can be address a word or a byte. Now, if you have seen, we have, for example, number of bytes or a number of bits. We have a number of bytes. If this is a byte or this is a byte, can it be also a byte or can it be a word? Now, if the address length is A and the unit is N, then we can easily found to the power of A equals to N. This is what we have learned when we talked about the number of words, the number of bytes per word. So, given the total number of bits in address memory, you can easily find the total number of bytes per word. Given the total number of bits in address bus, you can easily find the total number of bytes per word. Given the total number of bits in address bus, you can also easily find the total number of words in the memory, the total number of bits in the memory. We have the unit of transfer. This is the amount of data that can be moved in one read or one write operation. This may differ from word or addressable unit. We have external memory, like a disk, that transfer data in large data unit called blocks. Now, when it comes to external memory, they transfer data using what we call blocks. External memory transfer data in what we call blocks. They use blocks to transfer data. Now, what's next? We needed to talk about memory system. This time, we're going to talk about memory access method. What are the different methods that the memory used to access data? We have, for example, sequential access. Now, data are stored as a record in the memory, and we have to access this data in a specific order. This is a linear order. Now, we have these memory addresses. We have F1, we have F0, F1, F2, F3, F4, and so on and so forth, Fn. Now, for sequential access, we have data which are stored as a record, and access is done in a specific order, in a specific sequence. Now, we have address info, which separate a record, and they help to retrieve the data. Now, if we have got these F1 accessed, and we are using this sequence, the memory we have the idea that the next address to be fetched, the next address to be used to fetch data from the memory will be F2. Because we see F0 has been accessed, the next one will be F1. Then, after F1 has been accessed, we go to the F2. And so on and so on. So, one after another. Now, if the CPU wanted to get access to the data stored at the memory location F4, it has first to get access to the memory location F0, F1, F2, F3. That means the access is being done in a specific sequence, in a specific order. There is no way the CPU can get access to the data in F4 without getting access to the data in F0 or F1 or F2. So this is your 5-minute break. Take a break. We're going to resume class after break.